In this lecture, we're going to look at when fluids flow. In general, the flow of fluids is quite complicated. So we're going to focus on the flow of an ideal fluid. And what we mean by an ideal fluid, it has many restrictions. The first is that it's steady flow, or sometimes known as laminar flow. And that says that the fluid at a fixed point does not change its speed or direction with time. So it's not like the rapids where as the water collides with various rocks, that if you look at one particular point, the water may change its direction or speed as time goes along. It also means that an ideal fluid is incompressible, so we are dealing with liquids and not gases, for sure. The third restriction is that the fluid is non-viscous. That means that it flows without sticking to things. Honey is an example of something that is very viscous. It tends to stick to everything and it flows slowly. Viscous drag is the fluid version of friction. So we're looking at a case where there is essentially no friction as an object flows, as the fluid flows past some other object. Finally, there is no rotation of the fluid as it flows. And if you're looking at a pipe with water flowing through it, here we have a little particle of water in it, and no rotation means that particle of water goes from left to right following the arrow with time without changing its orientation. It's not this, where the particle of water tumbles or rotates about its center of mass. Streamlines are the path traced out by a particle of fluid in the flow. Streamlines do not cross because that would mean that a particle of water at the cross would have two different velocities, so that can't happen. Here's an example of streamlines as the flow of water or some other liquid encounters a cylindrical obstruction, the red circle. We see that the streamlines bend as they go around the obstruction, and so you can see that the particles change their direction and perhaps velocity as they go around the structure, but they do not cross. Okay, let's look at the continuity equation or conservation of mass when we look at this ideal fluid. Volume 1, the blue block on the left, is given by A1 times V1. So that's the area of the pipe on the left, times the velocity at point 1, times a certain time that it's going to take for that block to travel, in that how long it takes it to pass that point 1. V2 is similar. It's now the block on over there about to exit the pipe, times where it's the area 2 times its velocity in that part of the pipe times delta t. V1 has to be equal to V2 since as the volume 1 pushes into the pipe, volume 2 has to leave since it's an incompressible fluid and mass is conserved. So that as 1 moves in, 2 moves out, and they have to be the equal volume moving in and out of the pipe. So A1 times V must be equal to A2 times V2, so the delta T's cancel. And that's equal to some constant value, what's called the volume rate, capital R. The one result of this, since A1 is smaller than A2, that means that V1 is greater than V2 since they have to be equal to a constant. Let's take an example of this. Velocity of blood in blood vessels, for example. A blood vessel branches into 2 vessels. The areas of the 3 vessels are measured, and the velocities in the branches 1 and 3 are measured, but we want to know what is the velocity in branch 2. You might imagine that branch 1 and branch 3 are big enough to put in a probe so we can measure the velocity of the blood in those branches, but maybe branch 2 is too small for our probe. In this case, the conservation of mass, or continuity equation, requires that the volume 1 equal to volume 2 plus volume 3. So what enters on the left has to be equal to what leaves on the right. So we put in our area 1 times the velocity 1 is equal to area 2 times velocity 2 plus area. Solve that for velocity 2, and we have the answer we wanted.